Okay, maybe we can get started. Hello, everybody. Welcome to the Ottawa course on Introduction to Lie Groups and Quantization. This is a cross-listed course at Ottawa, and both graduate students and undergraduate students take it. We have a mix here. And the course will cover topics related to Lie groups, starting from the classical theory, which has more analysis in it, and then it will move forward to more algebraic things. So first to Poisson Lie groups and then to quantum groups. I'll talk about some more kind of modern topics, modern ways of studying algebraic objects and objects in representation theory and algebra connected to Lie groups are kind of originating from Lie groups and classical Lie theory. So we also, for Ottawa students, we also have students from other universities in Ontario joining. They will participate in this course virtually. Let me first mention that Ottawa students have to register through Fields Institute for this course, and you will receive, everybody will receive course material through the Ottawa version of Brightspace, which is called Moodle. So when you register with the Fields Institute via the link that I provided on Brightspace, after a few days, you will be added, well, hopefully after just a couple of days, you will be added to the Moodle, and you will get information about Moodle access with user and password and so on. And then you can just get whatever you used to get from me or from other professors as on your Brightspace through Moodle. That's what this would be: assignments, lecture notes, the link to videos of lectures, and your grades. Okay. So please register, because I will not provide anything on Brightspace. I will just do everything on Moodle. I'll not duplicate it because that will be confusing. All right. Now, what I'm sharing is an external web page for the course. There's a link to this on Brightspace. I'm sorry, on Moodle, so you can get access to this, to the link, to the URL that takes you to this. This is under my webpage. If you just also search my name, this will take you to my my webpage at Ottawa, and then you just click on teaching. You'll see this course. You just click here. That's another way to get to here. And this is where you find a lot of information about the course, including the references. So primarily in the first part of the course, I will follow more or less this book, which is a classical book on Lie groups and representation theory. But then at some point, we will diverge and talk about topics for which it's not easy to find one textbook, because I'm going to use a couple of references and it's more advanced. So technically, you can find everything in this book, but this book is huge and it's an advanced book. It's a great book to have and to read, but I will not be covering a large part of this course, a large part of this book. I'll just be covering here and there, different sections, of course, making sure that all the prerequisites are met. So that's about references and about the topics that are covered. Here you will find the breakdown of the lectures. So what topics will be covered in each lecture, including today. And the section numbers refer to the ones without a CP, they refer to the book by Brian Hall. The topics are close to what is covered in that book. And then when I have CP, these topics are closely related to what is covered in Chari Pressley in these sections. But then there are other topics which come from other references, especially in the last couple of lectures. And I do not, I mean, I will provide lecture notes for them, so they're not directly coming from any reference. Okay. And as for the policies, here are the course policies. This is the breakdown of your grade. There will be a 3-hour final exam, which for Ottawa students will be an in-person exam. It will be scheduled by the Office of the Registrar. And also the midterm exam will be an in-person exam given here. For students outside Ottawa, the exams will be virtual, but the duration will be the same, maybe with a few extra minutes just for the compensation for the time for uploading and downloading and so on. But that's how the exams would work out for them. And there will be also a total of 4 assignments, which will be posted on Moodle. I'll provide a LaTeX file as well, and with some instructions on how to complete. So you write your solutions in LaTeX. At this stage, that you are in your education, it is expected that you can type your solutions. And in fact, it's a great experience. It will be a very useful experience in other places, not necessarily typing assignments for other courses, but when you want to write a report, or if you decided to continue graduate studies, that's for undergrad students, if you want to write a thesis. So you should have latest skills, and the expectation is that you will type your assignment solutions, but I also provide some instructions on how to do this, and I'll provide a template so you could actually complete. All right, so the assignment due dates are also posted here. You can see this on this calendar. Everything is really on this calendar. The midterm date is written here. It will be an in-class exam. And so that's basically about the logistics of the course. Are there any questions about the logistics before we start talking about mathematics? Anybody has any question? So the main thing, again, for you Ottawa students, some of them just arrived, you should register through the Fields Institute. There's a link on Brightspace. I sent an announcement a few days ago, and you should have it. So you go on Brightspace, look at the announcements. There's a link. You register there, and then you will be added to this system called Moodle, which is like a Brightspace, but run by the Fields Institute. So that's the idea. Okay, so students from outside Ottawa, feel free to switch off your switch on your microphone and ask questions throughout the lectures. I'll look at the chat from time to time, but because I'm working on two monitors, basically, one that I'm using for sharing and the other one on my tablet, I might not see your chat questions immediately, but feel free to interrupt and ask questions throughout the lectures. We hope that we can make this as interactive as possible. And this is really what a graduate course is supposed to be. It's great that you Ottawa students are here in person, but for those from outside you Ottawa, we hope to maintain that level of interaction as much as possible. All right, any questions? Are there any questions? People from other universities? If there are no questions, then we can actually talk about the mathematics of the course. So in this course, as I said, I will begin by talking about the fundamental theory of Lie groups. So what is a Lie group? A Lie group is basically just a group, but with some topological structure associated to this. So let me share another screen and start doing serious mathematics now. Stop share here. Okay. So basically, in this course, we are interested in groups which are more like the group of n by n matrices with invertible, with non-zero determinant. So like GLNR, and that's like a prototypical example of a Lie group. It's the group of all n by n matrices with non-zero determinant. I could do this over any field. Instead of R, I could use C or anything else. And so as you see, this is a matrix group. So it's given by matrices. The operation of this group is matrix multiplication. So it's a matrix group. And in this course, we mainly study Lie groups which have realizations as matrix groups. Even though Lie groups don't have to be matrix groups, and we can study them more intrinsically by looking from the point of view of manifold theory, but the majority of examples that occur in various areas of mathematics are indeed matrix Lie groups. So the primary focus of this course, which makes life a little bit easier, is to study matrix Lie groups, okay? So now, what are the features of this group? Why should we call it a Lie group? What is the specific that was of interest to Sophus Lie, who created this theory? So Sophus Lie, so the Lie group, the term Lie group refers to the name of the Norwegian mathematician Sophus Lie, a 19th century mathematician, who created this subject. Of course, Lie didn't call these groups Lie groups. He called them continuous groups. And that's really the nature of these groups. So there's some sort of a continuous structure within Lie groups. So you see that what we have here, you can talk about matrices. You can just dilate matrices. You can do a lot of algebraic operations with matrices like exponentiation, conjugation, and deform matrices by some parameter. You've seen this in many of your courses, in like applied math courses or linear algebra and so on. So this is the sort of continuous nature of these Lie groups. And we are interested in groups which sort of inherit this continuous nature. Okay? So as I mentioned, we think about this GLNR as a subset of this MNR. I could use M, like maybe I should do math MNR or MNR. I mean, maybe the easier notation would be MNR. So maybe I just fix my notation here. N by N matrices, okay? And what we know is that we have a vector space here, okay? But that's not just a vector space, it's also a normed space. We can talk about distances here, okay? And as a normed space, well, there are many ways to put a norm here, but it's equivalent to Rn squared. It's like a, it is n squared degrees of freedom here, like there are n squared entries in the matrices. So that's what it is. So now, what type of group should be a Lie group? What else do we expect from a Lie group? What we expect is that it is a closed subspace of GLNR. Okay, so here's our first definition for the core. So this is the definition. So a matrix Lie group is a subgroup So we can do GLNR or GLNC, but let's first do GLNC. So, I mean, doesn't matter. I mean, we can be more specific later on. I'll clarify when we use GLNR and when we use GLNC. But for the moment, let's take a subgroup of GLNC, okay, which is, oops. Closed in the induced topology from MNC. So what is the topology of MNC? You can describe it as a normed space. You could say that the distance between two matrices in MNC, it's the sort of Euclidean distance, Aij minus Bij bars, like absolute value squared. And this is a metric. So you can talk about the notion of an open ball. So you can give a topology, the Euclidean topology. Or more conveniently, you can say that it's like you can talk about topology in terms of the notion of convergence. It will be equivalent because we're in a metric setting. So you could say, so equivalently, we could talk about convergence of a sequence of matrices to another matrix. So we say a sequence AN converges to A. So these ANs are matrices. Maybe too many N's. Maybe I should use a different letter. Maybe I should use A. So again, I'm choosing MNC, so maybe I should stay with my own conventions. It doesn't matter. Okay. If for each pair of IJ, the IJ entry in the sequence converges to the IJ entry in A. So this is convergence in C, of course. Convergence of numbers, okay? All right. So then in this language, a matrix Lie group will be a subgroup of GLNC with the property that any sequence of points in this group converges within GLNC to some point. Or equivalently, if it converges to something in MNC, either it's in GLNC or the limit is not in GLNC. Okay, so okay, maybe I should write it as follows. So equivalently, equivalently, G is a group, a subgroup of GLNC is a matrix Lie group if it satisfies the following property. For every sequence, like AK, where AK is in G for all K, if the sequence has a limit in MNC, so if AK converges to A in MNC, then either the limit is in G or it is not in GLNC. Okay, so this is another way of describing a closed subset of an open subset. So this is like, you can talk about it as like a intersection of an ambient closed set with an open set, or like in terms of convergence of sequences. You can see that this is the same. Okay, so let's now look at some examples, some other examples. You have a question, Simon?
So are there subgroups that are in that's so are there ones are there sequences that don't have their limit in GLNC?
Well, first of all, the sequence can go to infinity. Secondly, it's possible to have a dense subset. Okay, so I can give examples. I'm just going to give examples momentarily. So here's an example of a Lie group first. So we just saw GLNC as a subgroup of GLNC, but let's now take this example. G equals the set of 2 by 2 matrices of the form T 0, 0, T squared, where T is in C star. So this is a subgroup. It's not difficult to see with respect to matrix multiplication. You have a subgroup. And now, why is it closed? Because if you take a sequence that converges, then each coordinate should converge. So either the T's converge to 0 or to something non-zero. So if we say take a sequence of elements like oops. So if we take a sequence of elements like Gn in G of the form Tn 0, 0, Tn squared, then either the Tn's converge to 0 or the Tn's converge to something non-zero. Okay, and if they converge to something non-zero, then in the limit, you also get another matrix of this form with the limit not in non-zero, it's in C star. And if you converge to 0, then you actually get an element which is not in GLNC. So this is with respect to the second definition. I mean, you can check. This is an easy exercise for anyone who has had a second-year course in analysis to check that what we have is a closed subgroup, is a closed subset of MNC, or a closed subset of GLNC, more precisely. Okay, which means the intersection of a closed subset of MNC with GLNC. Okay, now here is another example which shows that we can have subgroups which are not matrix Lie groups. Okay, so let's take, for example, G equal to GLNQ. which means matrices in GLNC such that their entries are rational numbers. Okay. Even if you do it for GL1, so like you get a subset of C star. So if n is 1, what you get is Q star, non-zero rational numbers inside complex numbers. So we know that we get a dense set. And by non-zero rational numbers, you can converge to non-zero irrational numbers. So they are, strictly speaking, inside C star, but they're not in the subgroup anymore. Okay, so this is not a Lie group. Even though it's a very interesting subgroup of GLNC, it's not a matrix Lie group. Okay. Now, there are, in principle, two types of Lie groups that are interesting in mathematics. Like there are major classes of Lie groups. One class is the class of so-called reductive Lie groups, and those are groups which are closely related to GLNC in the sense that they have some matrix descriptions which are given by some kind of natural polynomial conditions. So here's one example, the special linear group. So maybe I should have mentioned the GLNC or GLNR. They're called the general linear group. That's where the G stands for, GL, general linear. And therefore, the special linear group should naturally be called SL. And you can talk about SLN over any field. We could talk about SLNR or SLNC. In this course, we're primarily interested in R and C as the base field, okay? Because this is a course with roots in analysis, okay? So what is this group? So SLNC is this subgroup of GLNC that consists of matrices with determinant equal to 1. Okay, and now SLNC is also a matrix Lie group. So basically, we need to see why it's a closed subgroup, or rather, a closed subset of GLNC. But that's because, so okay, can anyone explain why? Why is it closed as a subset of this open set GLNC with induced topology? This should be easy to explain. Okay, but why is this so? This you're basically giving me the definition, but why does this hold? What is really the reason it holds for this and not for some other example? What is it?
Because the determinant is continuous.
That's right.
And yeah.
Yes, thank you very much. So the point is that the determinant is a continuous function of the entries. Okay, so the determinant is a continuous function of the entries, and therefore, if you take a sequence of points on which the value of the determinant is 1, in the limit, it should be 1 because limit and evaluation commute for a continuous function. That's basically the reason. Okay. Similarly, GL and R, SL and R is a matrix Lie. So here, maybe, okay, well, we can think about SLNR as a subset of GLNR and call it a matrix Lie group, but we can also think about it as a subgroup of GLNC, but still closed there because being real is also a condition that determines a closed subset. So there's like Rn, so to speak, is a closed subset of Cn with the induced topology. Okay, so that's the reason. All right. So strictly speaking, if you want to use GLNC to define Lie groups, it's still okay. All right. Now, another important example of matrix Lie groups is the unitary group. This is a group with a lot of application in physics and nowadays in quantum computation. So what is this group? This is the subgroup of GLNC that consists of unitary matrices. So what is a unitary matrix? You should know from the linear algebra. That's right. So the condition is that AA star is identity. So what is A star? So here A star just means, as usual, it means bar transpose. Okay. And now, why is it a matrix Lie group? Again, we have to check that we have a closed subset of GLNC. And that is because this relation, it is a polynomial in the entries of A and their conjugate. And you know, any polynomial is a continuous function. So now if you want the polynomial to vanish, you're talking about a closed subset. Because it's like the inverse image of 0. And continuous functions, the inverse image of a closed set under a continuous function is closed. Okay. So again, it has to do with the continuity of the relation that describes it. Okay. Here's another example. So we talked about the unitary group, and the unitary group is a subset of GLNC, but we can always intersect this group with SLNC. Okay. And we get a new group. It is a matrix Lie group because closedness is inherited from the two. UN is closed, SLN is closed in GLN, so the intersection will remain closed. So it's a matrix Lie group, and this is called the special unitary group. The important example, SU2, it's related to the standard model particle physics. A lot of particle physics is related to representation theory of this group, and it's also related to quaternions, quaternionic numbers. Does anybody know the connection between SU2 and quaternionic numbers? From those outside Ottawa? Let me see, there's something in the chat. Okay, thanks for answering my question, Noah. Previous question. So the connection with quaternions is that, in fact, the unit quaternions of norm 1 form a group, and that group is just SU2. But we will get to this stuff later, okay? All right, so I talked about SUN. Now, we talked about UN as a matrix relation, unitary matrices, but it's also good to think about this as a group of isometries. So how can we think about UN as an isometry group? So first of all, what do we mean by an isometry? That's right. So it should preserve some sort of a distance. And typically we expect that it preserves a distance that comes from an inner product. So let's take the standard inner product. So we consider the inner product. This is a Hermitian inner product on Cn. It is defined as follows. The pairing xy is defined to be sigma xi yi bar. for x equals x1 to xn and y equals y1 to yn. So x and y are in Cn, okay? All right, the usual inner product, Hermitian inner product. It's a linear with respect to the first entry and conjugate linear with respect to the second entry. This is important to note, okay? So I, in the second component, I comes out as minus I, all right? And now, here is an important fact from linear algebra, that for any n by n matrix A, AXY equals x comma A star y, where star is the bar transpose that we defined above. So I leave this as an exercise. The proof is just one line. I mean, you just have to write each side in terms of entries. So you could, for example, choose x and y to be a standard vectors. The EI is the standard vector, standard basis, and write each side and see what it is in terms of the entries and use the conjugate linear property and see that this is true, okay? And now, as a consequence, we have the following proposition. For any element of A and C, M and C, the element is unitary if and only if. So I write if with two F's as if and only if. It's an isometry of this Hermitian form. If and only if. Maybe, okay, so here, okay, maybe I changed my mind because I want to put it in the next line. AX, AY equals XY for all X and Y in Cn. So this relation is in principle equivalent to the relation which is like AX squared equals X squared. The point is that XX is just norm X squared, and this is AX. And now here you see why that relation is referred to A being an isometry, because it preserves distances this way, okay? Okay, so now, so this is the assertion. The assertion is that being an isometry with respect to this Hermitian form is the same as A being unitary, okay? So now what is the proof? The proof is now again one line. So let's take A and M and C. So then we start from the left-hand side. So AX, AY. This is equal to X, comma, A star, AY, right? And now if we have okay, maybe I could prove it in like two steps. First, like let's assume this is unitary. So then A star A will be identity, and that proves that this is an isometry. So conversely, from AX, AY equals XY, it follows by the same trick, it follows that X, comma, A star A, Y equals XY. And now you can choose X and Y to be the standard basis. So choose now. So now we choose. The vector will be the one in the ith position, and Y equals EJ. And we obtain that the IJ entry of A star A is 1 or 0, depending on whether I is equal to J or not equal to J. Okay. So this is the proof. Any questions? Maybe I just zoom out a bit so you could see the proposition and the proof. So we just realized the unitary group as a group of isometries. So now we can think about other types of bilinear forms of interest and see what their isometry groups are. Okay. Okay. So this is now thinking about the so-called classical groups in uniform way. Are there any questions before I proceed? Everybody's following? Is it all trivial? Is it all clear to everybody? Trivial? Okay. Is it familiar to everybody? How many people, how many of you have seen UN and so on? Okay, not everybody. So I guess it's good to continue this discussion. All right. So hopefully we will get to more interesting things very, very soon. All right. So here's another example. So let's now, instead of taking a Hermitian form, we can take a symmetric bilinear form. Okay. And that will give us the orthogonal group. So what we take, well, first of all, you can describe this group in matrix form as the set of matrices in MNC with the property that X transpose is X inverse. And ONC is the isometry group of the bilinear form given by the standard formula as such. No bar on the second component because we want it to be bilinear, linear with respect to both coordinates. Remember, the previous form was antilinear with respect to the second coordinate. Okay. And this is technically the only example of an isometry group over complex numbers because all bilinear, all symmetric, all non-degenerate symmetric bilinear forms up to conjugation are equivalent to the diagonal one, to this one. You can always, in other words, you can choose a suitable basis so that they are written like this, okay? But that's not true over real numbers. So over real numbers, you have interesting examples. That's a consequence of the so-called Witt's theorem. So over real numbers, so orthogonal groups over R. So how do symmetric bilinear forms over R look like? We can diagonalize them, and then what do we get? Yeah?
Well, get ones and minuses.
That's right. You just get pluses and minuses. So they will all look like, so for P and Q such that, so integers P and Q, where the sum is N, so we can define the pairing xy to be the sum from 1 to P, xi, yi, minus I equals P plus 1 to N, which is P plus Q, xi, yi. Some pluses and some minuses, okay? Okay, so then the isometry group maybe I just put some PQ here. So this is called the group OPQ. Okay, the orthogonal group OPQ. And it is important in quantum mechanics. It's closely related to what's called the Poincare group, if you've heard about it. Okay. Now, here is a remark. Here's another way to describe groups of isometry. So here's a remark. In particular, I'll explain this idea with this example. So if we take this matrix, which is like block diagonal, with diagonal blocks, identity and minus identity, okay? So then, the pairing that I just introduced so that's just y transpose gx. Okay, so the book uses this notation x, y, and k, where in book's notation n is p plus q and p is k, something like this. This is maybe book's notation. Okay, but I mean, this is like more symmetric the way I write it. Okay, so now what is the consequence of this? The consequence is that the relation ax, ay, pq equals xy, pq. The fact that A is an isometry can now be written in a slightly different form. So you get y transpose A transpose G AX for the first one. And for the second one, you get y transpose GX. Okay? So now you have two matrices here. One of them is the G, the other one is this matrix. And y transpose the matrix X gives the same value for all choices of y and X. Well, what does that mean? Then these two matrices should be equal, because you can choose the y to be some standard EI and the X to some standard EJ. You're basically looking at the I comma J entry on both sides. So they should be equal, okay? So it follows. Or maybe I could just like do an if and only if, because in fact it's an if and only if. That A transpose GA equals G. So A is an isometry with respect to this PQ bilinear form under real numbers. So maybe here I should have specified. Did I specify? Maybe I should specify that X and Y here are in Rn. Okay. I think I kind of mentioned over R. I didn't mention that the X and Y are in Rn. Okay, and therefore this matrix A now it's like in it's in GLNR. Basically, for this remark and this example, we'll be working over R. Okay, so the consequence is that we get a matrix description of these groups OPQ. Okay, so if you wanted to write this group as a matrix, this is the trick. So this OPQ is the set of matrices in GLNR with the property that A transpose G A equals G. So if I set Q equal to 0, then I am expecting the orthogonal group, which agrees with this formula. I get A transpose identity A equals I. Okay, so this is a more general sort of family of groups than the orthogonal group, ONR or ONC. Okay, so, and you do have a nice description as a matrix group. So this isometric group is easy to describe by matrices. These matrix realizations are extremely important in general in algebra representation theory and so on. There are a lot of things that you first discover by matrix realizations, and then you develop into a theory that uniformly extends using all these combinatorics of root systems and so on in a uniform fashion to the class of reductive groups. But matrix realizations are extremely important. Okay, any questions so far? Everybody following, hopefully? So we just looked at a lot of examples. Let's continue, because these examples are just the primary reason the subject was developed and explored vastly. So the next example would be the symplectic group. So remember that we decided to explore isometries of different bilinear forms, and so far we only looked at ones which are symmetric or symmetric up to conjugation, but we can talk about antisymmetric bilinear forms. They're called symplectic forms. When they're non-degenerate, they're called symplectic forms. So here the expectation is that yx is not equal to xy, it's equal to minus xy. Okay, so now let me give you a sort of an explicit example. So here, if you want a non-degenerate form, you have to assume your vector space is even dimensional. So we consider on R2n, or we could do C2n. Maybe I just rewrite this. So on R2n or C2n, we can consider this bilinear form. Summation starting from 1 to n, xi, yn plus I, minus summation from 1 to n, xi plus n plus I don't know, either way, yi. Yep, it's good. Yeah, all right. So now you can check. It's very easy to check that yx is equal to minus xy. All right. And now we can consider the group of isometries of this bilinear form. So you can see that, in fact, this bilinear form, like any other bilinear form, can be given in such a form for a matrix G. But what is that matrix G? What do you expect from that matrix G? So here you saw that that matrix G is a symmetric matrix. But if the form is antisymmetric, you expect the matrix to be a skew-symmetric matrix. So here, in fact, you can see that xy equals y transpose gx for the matrix G equal to 0 in minus in 0. It's an antisymmetric matrix, okay? And now, okay, maybe just to conform more with the notation of the book and also my notes, maybe I should just use like this omega. All right. Maybe here omega. Okay, omega xy is defined as such. And now, the symplectic group is just the group of isometries of this form. So SP 2 and R is just a set of invertible n by n matrices with entries in R, which preserve this form. Okay. And this is a group which is related to symplectic geometry. Those of you who are interested in geometry, maybe symplectic geometry, which is also another subject closely related to quantization. This group shows up in symplectic geometry a lot. Okay. All right, and this is another example of a matrix V group. Okay, any questions so far? Okay, let me see. Let me check the chat. Do we only study the group of matrices over fields? This is a great question. In this course, we do not look at groups like SL and Z, which means matrix groups over rings rather than fields. But these groups are also extremely important, not only in algebra, but also in number theory and in dynamical systems. So there's like vast literature on these groups. The connection to number theory is that the theory of modular forms expects, or rather studies, complex functions with invariance property with respect to groups like this. And the connection to dynamical systems is that typically you're interested in groups, or rather in spaces, which look like a quotient of a matrix Lie group by one of these groups. So the point is that this is not a Lie group because it is discrete. Just like Z is sitting discretely in R cross, as it's like with respect to topology, it's discrete. Okay, it's closed, but it's discrete. Such groups also sit discretely in here, and these quotients have now a nice description. So this the kind of simplest case where n would be 2, you will get this picture, which you have seen probably with a lot of circles. The fundamental domain of SL2Z, or like SL2R mod SL2Z. Okay, so that's like a familiar picture. Maybe I can find it on the web and show it in the next lecture. But yes, from our definition, such groups will deserve to be called matrix Lie groups. But the problem with these groups is that the connected component of identity is trivial. We will, as we proceed further, hopefully by the end of today, we learn that we would like to focus on connected Lie groups, because we expect this continuous feature, or rather this continuous properties from groups. And for that, we need the group to be connected so that we can actually move along points on paths. Okay, so we want the group to be path connected. And the SLNZ is not a path connected group, although it is an extremely important and extremely well-studied group in algebra and number theory. Okay, but thanks for asking this question. Okay, so that's what the symplectic group is. And now, well, we can take the symplectic group. Okay, so should I talk about maybe compact groups first? Maybe I should talk about compact. There was another example I want to talk about. Okay, so here's another important example. So the case where n equals 1. So the symplectic group for n equals 1. It's a subgroup of GL2R. It's a subgroup of 2 by 2 matrices. And in fact, it happens to be isomorphic to the special linear group SL2R. Okay? So the general statement is that SP2R or SP2C, all right, is isomorphic to SL2R or SL2C correspondingly. Why is that so? So let's see why this happens. So what is SP2R? Well, it's the isometries of this bilinear form. So what is the bilinear form? So the bilinear form will be on R2. Let's represent the coordinates by x1 and x2. And if I take another vector y1 and y2, what is this pairing? This pairing looks like x1, y2 minus x2, y1. So what do you see here? What does it look like? That's right. Looks like a 2 by 2 determinant. Okay, that's the only determinant for which there's such a simple, nice formula. And in fact, if you take A to be the matrix Aij, then if you compute omega Ax Ay, well, what is Ax? It will be just the linear combination of the columns with the coefficients. All right, maybe it's easier. Maybe it's easier to compute. Maybe it's easier to compute the following. Maybe compute omega A E1 A E2. So E1 is 1, 0. E2 is 0, 1. So the first one will be just the first column, which is like A11 E1 plus A21 E2. The second one is A12 E1 plus A22 E2. And now when you expand and use this formula to simplify, you actually get this determinant A11 A22 minus A12 A21. Okay, so now if A is supposed to be an isometry, then we should have this relation. But what is omega of E1 and E2? That's just 1. Okay, so if A is an sp2, then we will have this relation. Okay, but this means that the determinant is 1. And you can see that, in fact, any other relation imposed by isometry basically boils down to this. Okay, so this is really if and only if. Yeah.
Could you make it bigger, like maybe having
Make it bigger. All right. Let me see. What is the? Oh, maybe it's because of the chat box. Okay. All right. So now I shouldn't maybe change the, because I shouldn't change my borders. Okay. Is it okay now? Right? Okay. Okay, maybe a bit larger. So I just verified that if A is an isometry, it's an sp2, then its determinant is 1. But you can actually reverse the arrows. You can see that, in fact, this relation is sufficient for A being an isometry. Okay, that's because here only have 2 vectors. I mean, well, in order to check that A is an isometry, it's enough to check it on like pairs of basis vectors. But then another pair of vectors would be like omega A1 A1. This is always 0, which is equal to omega E1 E1. Okay, omega XX is 0 because the form is skew symmetric. So omega of XX is always like minus omega XX, and so omega XX is 0.
What is?
Yeah, question?
Yeah, for purposes, does it matter what non-degenerate means for symplectic? Of course, like for a quadratic form, that means it's degenerate. How would it?
What's the definition of degenerate? Maybe I should have given that before. I was assuming that this is a familiar concept. So non-degenerate, so a form is called degenerate if it has non-zero radical. So what is the radical of form? So maybe it's okay. So maybe just a remark. So the radical of a form so it's basically the set of vectors V such that V is 0. Suppose the form is symmetric or skew symmetric. It doesn't matter if I put the V in this component or in this component. It will give the same subspace. And the form is non-degenerate if it has no radical. Equivalently, if you write a matrix that describes that form, that matrix is invertible. The matrix that gives you the Y transpose AX formula. Okay. Any other questions so far? Okay, so now what we learned is that like sometimes you have some exceptional isomorphisms between the so-called classical groups that are given as isometries of vector spaces. Okay, so there's a few more exceptional isomorphisms, but these are also very important in lead theory. I think SL4 is the same as SO5. So I think so. These things you can check. SO5 is isomorphic to SL4, and okay, SO6 is the same as SL. I'm sorry. So maybe did I make a mistake here? So I think SO6 is the same as SL4, and SO5 is the same as SP2. Okay, so with this notation, I should say SP4. Sorry, SP2 was SL2. Okay, so SP4. So we have these exceptional isomorphisms. These can happen. But now you can ask me how you know these things, because I think about these things from the Dinkin diagram point of view, and that's much easier. Okay, but you can try to find some combinatorial, some sort of a matrix isomorphism like this. Okay, I mean, that's a challenge. Okay, so let's continue. So now, so we looked at some examples of Lie groups. And among these Lie groups, an important place is taken by the so-called compact Lie groups. Okay, so just like compact topological spaces, which are nice, compact Lie groups also exhibit a lot of interesting features. Okay, so compact. So here's, let's say, talk about compact Lie groups. Compact. Okay, maybe I talk about compact groups in general. So a subgroup of GLNR or GLNC is called compact. It's called a compact group, or a compact Lie group, if it is compact in the induced topology. Some of the examples that we just looked at are compact. So let's see which ones are. So for instance, UN is compact. So why is this so? Well, compact by Heine-Borel, because we are in a metric space, by Heine-Borel, we know that compact is the same as being closed and bound. Okay, so enough to verify it's closed and bound. Okay, but this time you have to verify that it's closed in the full space. Okay, but again, that's just because it's given by a polynomial function, by a function of like z and z, like the entries or their complex conjugates. So the closedness is just a consequence of being the inverse image of number one for a continuous function. And what about boundedness? Well, that's because being unitary means that in particular, each column has norm one. Okay, so being a unitary matrix, each column is a unit vector, and the columns are also orthogonal to each other with respect to this canonical Hermitian inner product that we just described. Okay, so now if the norm of the vector is one, it's really on a sphere, so that's really a bounded set. You have a question? And what is your name? Ying. Okay.
So if we already know a group is a Lie group, then can we check if it's bounded to see if it's a compact group?
That is right. That is right. Yes, yes.
But yeah, we need to be close to that. We need to be close to that, and then
That's right. It should be a closed, but it should be a closed subset of elements. Okay. Okay. So now, I mean, that's because, if you take some open disk, the interior of the open disk is closed in itself, and it's bounded, but it is not compact. Okay. Your space should be complete for this Heine-Borel to be true. Heine-Borel, you learned it for Rn, and therefore you should apply it only for Rn. So you should check the closeness inside M and C, not inside GL and C. In other words, that's not automatic.
Well, because the definition for Lie group is already included closed in MM.
Well, that's exactly what I'm saying. So being closed in an open set is not enough. So well, okay. So what is the statement of Heine-Borel? So Heine-Borel is about subsets of Rn. It's not about subsets of an open set.
Oh,
Okay, so it is like, think about this example. Think about the inside the open disk of radius 1. It is closed inside itself and it is bounded, but it's not a compact space because it has a sequence which doesn't converge to anything. Okay, but any compact space has the property that any sequence has a subsequence converging to something. Okay. All right, so now how much time do we have? We still have time, right? Okay, which is great. We have 10 more minutes. Okay, so now UN is compact. We can now think about, let me see, now I have to make a choice here. Okay, so now O and R is also compact. And that's just because, so why is it compact? Because O and R is really the intersection of this compact set with GL and R. Okay, so this time compactness inherits because this is the intersection of compact and something close. Okay. But what about O and C? Is this compact? What do you think? Is it compact? O and C is not compact. Okay, so you have to be careful. And why is that so? I'll show this by an example. Let's think about O2C. So it's the set of matrices of the following form. X, Y, Z, T with X squared plus Y squared equals 1, Z squared plus T squared equals 1, and XZ plus YT equals 0. Okay, so these relations describe the condition A transpose A equal to 1. First, you know, the first row, first column should be 1, but that's really like the inner product of the first column by itself. It should be 1. The inner product of second column by itself should be 1, and the inner product of the two columns should be 0. Okay, so that's what it is. And now we can consider matrices of the following form. X plus IY, X minus IY, X minus IY, X minus X minus IY, with X and Y in R, and X squared minus Y squared is 1/2, which is basically a hyperbola. Okay, so you can check that these conditions, okay, maybe, I don't know, maybe I should, maybe I should change them because I use X and Y above. Maybe I should use alpha and beta here for better clarity. So you can check, for example, what's the inner product of the first row by itself? It's like alpha plus I beta squared plus alpha minus I beta squared. When you expand, you get the 2I alpha beta and 2I alpha beta that cancel each other. So you get alpha squared minus beta squared. Should I set it equal to 1? Maybe. I get 2 alpha squared minus 2 beta squared, which is 1. Okay, and same thing happens for the other. You can check that, in fact, such matrices are contained in so therefore these matrices are in O2C. Okay, so I use the mixed notation. Maybe I should just use O2C. Okay. Okay, all is good. But now you can see that, well, this is a hyperbola, so this alpha and beta can go to infinity, and as a result, the entries of this matrix can go to infinity. Therefore, this cannot be compact. Okay? So O and R is compact, but O and C is not compact. That's a surprise, isn't it? Okay. What about the symplectic groups and how much time we have? We have maybe another 5 minutes. We can talk about the symplectic group. Well, the symplectic groups are not compact, but we can construct a compact subgroup as follows. So if we take, so this is called the so-called the compact symplectic group. So we can take this group SP2 and C that we just constructed, the isometries of the form on C2N, the non-degenerate skew symmetric form omega on C2N, and we can take its intersection with U2N, which we know is compact. So now this intersection will become compact. It's not difficult to check, and it's a subgroup. It's a matrix Lie group indeed, which we call SPN. For some reason, the notation doesn't quite agree. We don't call it SP2N anymore, just SPN for a reason, which I don't want to get into this right now. But anyway, this is a compact matrix group, compact matrix Lie group. Now, there is a description of SPN, which is closely related to quaternions. So I would like to give this description as the last thing for today. So let us consider, so here's another fun description. SPN. So at the moment, we just got it as an intersection, but it would be nice to have some matrix description of it, right? Because you cannot intersect these two things easily and visualize. So it's good to have some matrix description of this SPN. So let's take this transformation J. So J, oops. Should I write larger for those who are sitting at the end? You guys can see this, is it okay? Okay. So J alpha beta is defined to be minus beta bar alpha bar for alpha when beta in Cn. So two vectors in Cn can be put next to each other to form a vector in C2n, and I would like to define this map. Okay. So now what is special about this map? Why do I care about this map? Well, first of all, J is conjugate linear. So this means that Ji equals Ij. J is not a linear transformation of C2n. It's an antilinear transformation. It anticommutes. I forgot the -1. It anticommutes with I. It's R linear, but not C linear. Okay. Now, what does it remind you of? That's right. This should remind you of the quaternions. Okay. So now also J squared, it's easy to check that J squared is -1. This should convince you that there should be a connection with quaternions right now. Okay. And now here is a lemma. Recall this omega was this symplectic form that I defined before, right? Which was up here. If we go up here, I defined it over R, but we could do this over C, as I said. So this is the omega. Okay, I'm talking about this omega right now. Okay, so now let's come back. And it's something on C2n. I represent two vectors in C2n by Z1 and Z2. And the claim is that this is equal to the Hermitian inner product of Z1 and JZ2. Okay, so on this side, the inner product is like, I don't know, XY. It was supposed to be sigma XI by I bar. Okay. And on the left-hand side, I had this Hermitian inner product, and this is the role of the J. So J, the quaternions relate the Hermitian structure to the symplectic structure. And this is an important observation in symplectic geometry. Okay. All right, so what is the proof? The proof is really an exercise. I'll just leave the argument. Once you know that this holds, the rest is just linear algebra. Just write out both sides and see that they are the same. Okay. And now what is the conclusion? As a consequence, we get this proposition. That SPN, this compact symplectic group, we define as the intersection of the symplectic group over complex numbers. And UN, it is just the set of matrices in UN. I'm sorry, U2n, because it's 2n by 2n matrices. Unitary matrices that commute with J. Note that J is not C-linear, it's R-linear, but this commutation makes sense because elements of U2n are also R-linear transformations. I mean, we don't think about, well, I mean, they're C-linear also, okay, depending on the context. Anyway, they are R-linear. They're C-linear, so R-linear, okay? So what is the proof? The proof is, again, just kind of more or less one line. So let us take some element in U2n. So then we can start with omega of AZ1, AZ2. If A is supposed to be isometry, it should be omega of Z1, Z2. But what is this? Well, we know this is AZ1, JAZ2. And now we use the Hermitian property of this inner product. So this is just Z1, A star, JZ2. But A is unitary, so this is just Z1, A minus 1, JZ2. I missed an A somewhere, I think. Yeah. I mean, there's light coming and I don't see what I'm writing. So. Okay. So now compare. Or rather, maybe I should write, so this means that this relation, omega AZ1, AZ2 equals omega Z1, Z2 is equivalent to Z1, Z2 equals Z1 A inverse J A Z2. And now, by choosing the Z1 and Z2 to be the standard basis by the same trick as before, you know that this should be the identity matrix, which is equivalent to or rather, sorry. So this is, I'm missing something here. I'm missing a J somewhere. This is a J here. Sorry. I mean, the left-hand side is Z1, J, Z2. So then this right-hand side is J. And now this is correct. This last relation is equivalent to AJ equals JI, JA. Okay. So now you can write the matrices in U2N in block 2 by 2 blocks matrices of size n and get a matrix description of this SPN. Okay, so it's maybe time to stop. So today we saw a lot of examples of Lie groups. So this means that there should be some interesting theory to put all of these things together. And this is really the goal of the course, to develop a theory to analyze these examples and a lot of other examples of Lie groups of interest in a lot of areas of mathematics together. Okay. Are there any questions? Okay, let me see. There's something in the chat. GLNR is closed inside GLNR, but it is not closed inside n by n matrices. Because the determinant is only non-zero, and you can converge by matrices which are invertible to non-invertible matrices. I will post the first assignment hopefully by Friday.
The question of the definition of J. Define it as a function. Define it as a function. When you define J as a
Right.
function,
It's a linear, it's an R linear map.
so if you take your vector to 2n, it's C2n, and then cut it in half, and then that gives you alpha and beta.
Mm-hmm.
That's how.
Okay. I mean, it was given by this formula. Yeah, this is the formula.
And then what are alpha and beta? There are two halves.
Alpha and beta are two vectors of length n.
Cut your vector.
You just switch and then conjugate and change the sign of one.
Okay. and
That's
then
it's a map.
the J after the matrix acting on it.
Huh?
Yeah.
Well, this is a linear. This is a transformation from C2n to C2n, but only R linear. These are R vector spaces. Okay, so it makes sense as an R linear map. So you can, okay, I mean the construction is that you give it a vector in C2n, which is like of the form alpha beta, and it gives you another vector in C2n as shown.
Yeah, okay.
That's well defined.
But then after that, you use J as a matrix.
I mean, everything, I didn't really write any entries of matrices. I use it as a map or like a linear transformation or linear map, whatever,
Okay.
as a function.
Right. The other part, you use J as a function from C1 to C2.
Yeah, it's a function with some properties, in particular being R linear.